record. Okay. All right, we are skipping. Okay, shh, I'm not going to talk over you.
Not even talking, Miss Jason.
Okay.
We're skipping 2.2 and 2.4.
We're skipping 2.4, going right into 2.5. Don't worry, it's not on the final or anything. But, Evan. All right, postulate. Okay, this is important. This is, again, something that maybe you want to put on a note card, a flashcard. This is a statement that is accepted as true without requiring proofs. Okay, we're not at the proof part yet, okay? But postulates, we say them, and they're going to be so obvious. You're like, why do we even have to write this down? It's still important to know, okay? We need to know these postulates, what are going to lead into theorems, and then we're going to have proofs, and we have definitions, okay? So let's take a look. Again, when we think of a postulate, we think of something that's just really obvious. Okay, like something we don't have to prove. Okay, so the first one, through any 2 points, there is exactly one line. What does that mean? Can I draw another line through those 2 points?
Yeah.
Well, won't it be the same line?
Yeah.
Yeah. Okay, so I can keep trying to draw, here's my 2 points, I'm going to draw a line. Any other line is just going to be that same line. So that's why we say exactly one line.
What if there was a third point?
Well, look at the hypothesis. Remember, all of these are going to be conditional statements.
But wait, what if there's a quadrilateral between points P and R?
Okay. What I need you to think of these conditional statements, that means they can be rewritten in if-then form. Okay? So when we're trying to justify something, we're looking at how can we justify this? So let's think about this in if-then form. What's the first part, the hypothesis? If there are 2 points, just 2, then there is exactly one line that goes through those 2 points. Okay? I'm not talking about a third point. I'm not talking about anything with a plane. I'm just giving you, if you have 2 points, there's exactly one line through it. Okay? All right. Let's look at the next one. Now, did that seem obvious? Right? I put a point here, I put a point here. There's only one line I can draw through those 2 points. That's what that was saying. Okay, through any 3 non-collinear points, there is exactly one plane. So if you have 3 non-collinear points, remember we talked about the tripod, right? Why do we use a tripod for cameras? Right, it's more stable than having 4. So there is exactly one plane. This should be familiar. We've already talked about this from the previous chapter. Okay, next one. A line contains at least 2 points. So let's think. Can anybody raise your hand if you think you can write this in an if-then form? Ariel?
If there are at least 2 points, then there can be a line.
Okay, but what you just gave me was the converse, which is still a conditional statement, but Evan, give it a go.
It is a line, it contains it. Then it contains at least.
Right, so basically if you have a line, there has to be at least 2 points on that line, and actually there are infinitely many. So, right, so basically we're saying, okay, if you have 2 points on that line, then all the other, right, then R, right, it's going to have at least 2. Could it have 3 points, 4 points? Of course. All right, next we have a plane contains at least 3 non-collinear points. Doesn't that, it's almost like the converse of this one. This is saying if there is a plane, then it contains at least 3 non-collinear points. Okay, so picture, right? This wall is a plane. So I have to have at least 3 non-collinear points that exist on that plane. I know the wording is a little confusing, but that's, you'll see. It has to have 3 non-collinear points. How do we define a plane? With 3 non-collinear points. Remember, we can't have collinear. Think about, right, where does the ceiling and the wall meet? Along that line. So that line does not deter, right? That line is on this plane and this plane. But if I take 3 non-collinear points, then I'm just talking about the wall or I'm just talking about the ceiling. Good? Okay. Like I said, there's a lot of language in this chapter. Okay. We'll get to, it's like English all over again. Okay. 2 points lie in a plane, then the entire line containing those points lie in that plane. Okay, so, right, we got 2 points. So remember how I said the line's just going to keep going on forever and ever? But isn't the plane also going to go on forever and ever? Yeah. So is that line ever going to go off the plane? Nope. Okay. Again, did that seem obvious? Yeah. Okay. If 2 lines intersect, we've already talked about this, their intersection is exactly 1 point. Can they intersect at 2 points? No. We're talking straight lines, not curves, not circles, okay? They have to be straight. And the last one we've also discussed, if 2 planes intersect, the ceiling and the wall, intersection is exactly 1 line. Okay. Obvious? Okay. Now, how do we use these? We use these with our always, sometimes, or never. If a postulate can justify whether a statement is true, then it's always going to be true. But remember, we also talked about if it's sometimes true, we can come up with a counterexample. Okay, so that's how I want you to think of these. And never true also could have a counterexample. Okay, let's see. If points A, B, and C lie in plane M, then they are collinear. Anybody? Sometimes. I heard never.
There's no more. I thought it was sometimes it's never.
Let's think about this. Okay, always true, always true. Sometimes true means it could be true, but it also could be false. And the never true means it's never going to work. So what?
In the plane?
Well, they're just giving us points A, B, and C lie in plane M, then they are collinear. So what we're asking ourselves, if that hypothesis is true, does the conclusion have to be true? Let's think about it. You have 3 points lie in plane M. Do they have to be collinear? No. Could they be collinear?
Yes. Yeah.
Yes.
So sometimes. Right?
So it's sometimes.
Yeah, I know.
Good. All right. Next one. There is exactly 1 plane that contains non-collinear points P, Q, and R. Is that always true, sometimes true, or never true? And I will tell you, just so you know, these always, sometimes, or never are going to show up all year. And that's kind of what distinguishes honors regular, because you really have to think about the postulates, okay? And we always you saw some on the test. It's really easy to get hung up and get it mixed around, right? What do you think? Always? Well, did we have a postulate that pertained to that? Isn't a plane? There's exactly 1 plane. So if I pick 3 points in space, is there exactly 1 plane that goes through them?
Oh no.
Didn't we have?
No.
Through any 3 non-collinear points, there's exactly
Yeah, it's always.
1 plane. So it's always. I'm not trying to stump you. I'm just trying to get you to think, because when we get to the proofs, it gets a little more intense. So you really have to know these postulates and theorems and definitions.
Like right now,
We are going to do proofs today.
I don't want to.
Well,
I have to.
you have to. I mean, it's like a you problem then. Okay. I mean, we can't get rid of proofs in especially geometry honors. Again, that's one of the the at-level geometry, they do proofs as well. They just don't do as many on their own. Like they have more. They proofs. You'll see they have 2 columns, statements and reasons, and usually we'll give them more of the statements, and then it's almost like fill in the blank. Whereas we expect you in honors to be able to fill in both sides.
There are exactly 2 points to every one of It's never.
That's never. Yeah. Let's see. Because we had a postulate for that, and that was it had exactly one line, right? So it's impossible to get to. All right, plane ABC and plane DEC intersect at point C. We don't even have a picture, but we should be able to determine. Let's see. If two planes intersect, their intersection is a line. So you'll never get two planes intersecting at a point.
What if it's like a corner plane?
Okay, that would be three planes. Take, for example, the ceiling, the wall, and that wall. It's right there, that corner. Does that make sense? So three planes can intersect at a point, but not two. Two will always make a line. Okay, so those were postulates. Next, we're going to get into theorems. Okay, this is a conditional statement or a conjecture that has to be shown true. So we have to, just so you know, must be proved. Okay, what's a proof? Basically, you're going to have a logical argument where each statement is supported by a statement that is accepted as true. Okay. We'll get into some examples. So basically, when we come up with a proof, right, you have your statements and then you have your reasons. So the statements are referring to, like, angle A is congruent to angle B. But then over here, your reasons are always going to be definitions. Oops. So you're going to have definitions. You're going to have postulates. And you're going to have theorems.
Like the Pythagorean theorem? No, like.
So Pythagorean theorem is a theorem. A squared plus b squared equals c squared. There is a proof for that, right? We're not going to get to that for some time. We're going to start off with some basics.
What's the proof?
You'll see. It's hard to explain a proof until you've actually done one, okay? So we are going to do the proof of the midpoint theorem. And you're like, wait, we already did midpoint, but we didn't do the midpoint theorem.
Wait, what was the one?
Okay, the midpoint is the segment, or the midpoint of a segment divides the segment into two congruent segments. That's important. Congruent. Okay. So, remember from chapter 1, we did definition of midpoint. What was the definition? It divides the segment into equal parts. You're like, well, isn't that the same thing? Almost. Definition of congruent segments are equal segments, but midpoint theorem uses congruent. Definition of midpoint says the parts are equal. It's a very subtle difference. Questions? I know it gets a little confusing. It's almost the same thing. How is it different? You'll see on the proof on the next page. Okay, our very first proof. It's so exciting. Okay, the reason proofs can be a challenge is I can't teach you how to think, but I'm going to try, okay? How do we get from one step to the next, and how do we justify it? So the first thing we want to see with a proof is the very first statement is always what are we given? We have to start with something. So we're going to write M is the midpoint of PR. Yes, I know it's a bit to have to write. Don't just draw an arrow, write it in there. You can abbreviate midpoint. I'm fine with that. You know, if you want to just put, yeah, that's fine. MP. Okay, and then the reason I am just going to write given. You have to be given something to start with. Okay, now our last step, our last statement, also, you'll notice I'm going to number these. You know, I don't care if you put one and then a circle, one and then a period after it, or parenthesis. You have to make sure for every statement you have a reason. So that's why I want to make sure that you're numbering each one. Okay. So I'm going to prove this midpoint theorem using the definition of midpoint. Okay. I have to be provided something. If I'm trying to prove, right? Right. Like think about like a court case or something. Right? You have like, okay, this is what this person is going to court, right? And then you have like all the justifications why they're, maybe this person is guilty or not, right?
The given is the M is the midpoint.
Yeah. Okay, so what's the definition of the midpoint? They turns this into equal segments, right? So I'm going to say PM is equal to MR. And that's definition of midpoint. Do we agree with that? Yeah, Alec.
You could also say that M bisects PR.
Do we have anything in the given statement that says we have a bisector?
Yes. This is the midpoint. The midpoint bisects the line between 2 points.
So, but if we look at the definition of midpoint, do you see anything that says bisect? I understand what you're saying. It splits it into 2 equal parts. This is where proofs can be a little tedious. It comes down to the wording. It says equal parts. Now, after you know that they're equal, could you say that M is bisecting it? Yeah, but we don't need to do that. That's too much work. Okay. Questions? I know, it's really confusing because you're like, why do we have to write this?
How is PM equals MR the definition?
Okay, again, look at what I highlighted. What does the definition of midpoint say? It divides it into equal parts. So that means I can make PM and MR equal to each other.
And the reason why that's happening is because of the definition.
This is the reason.
Yes.
Okay, now, step 3. Well, if they're equal, doesn't that mean they're also congruent? Okay, so.
But that's what we were saying earlier, and then it wasn't.
Yeah.
Right, but here,
What?
once they're equal, we can say they're congruent. Why?
Because equal means the same as equal.
Definition.
I'm aware, but earlier it said that it wasn't. That was the difference.
And we just proved our midpoint theorem.
Why do you have to prove it?
Right here.
But why? What's the point of proving?
Okay, the very beginning proofs are kind of confusing. When we get into stuff like triangles, it actually gets a bit easier because you have to go based on what
The wording is.
so I can't use midpoint theorem to prove the midpoint theorem, but I can use definition of midpoint, which we learned in chapter 1, because definition of midpoint says they're equal. But then if they're equal, they have to be congruent. And now we're done. We just proved the midpoint theorem. This one was like, it's almost like too obvious that it's hard to, like, why do we have to do that? But it is necessary. Questions? Just looks confusing?
Are there any examples in the notes?
You can say that they're congruent before you say
What do you mean examples in the notes? Where in the notes?
That are less like weird than this, that are actually something we have to prove and not like
Well, let's look at the next one.
the next.
Okay. If you have, so here, let's take a look. We're going to complete the following proof using definition of right angles. Okay, so what am I given? Angle 1 and angle 2 are right angles. Angle 1 and angle 2 are right angles. And you can abbreviate. Sometime with angles, I'll just put like an angle symbol with an S. Okay, what am I trying to prove? That they're congruent. Okay, that's fine. So if this is again, the first proofs that we're going to do are kind of obvious. You know, you agree with that, right? The right angles are going to have to be congruent. Why? They're both 90 degrees. So I'm going to say measure of angle 1 equals 90 degrees. And then I'm going to put measure of angle 2 equals 90 degrees. How do we know that? Okay, so what did I say in the directions? We're using this as definition. Okay, now we're gonna do that next. Notice I put measure. Okay, anytime I'm using equal, I put a little m in front. Okay, so if they're both equal to 90 degrees, then they both have to be equal to each other, right? So I'm going to say measure of angle 1 equals measure of angle 2. We didn't get to all the properties yet, but this is simply substitution property. We're just going to say substitution. I'm basically, right, if two things are equal, I can substitute one for the other. Does that make sense? If this is equal to 90, I can substitute measure of angle 2 for the 90 degrees. That's all I'm doing there. Okay, we have one last step. If the measures are equal, doesn't that mean the actual angles are going to be congruent? Yeah, so I'm going to get rid of that measure. I'm just going to put an angle 1. I'm going to switch to my congruent sign. And I'm going to remove those m's. I know it's a subtle difference, but it's important. Okay, we're almost done with our proof. We've got the proof statement. Now we just need a reason. Definition of congruent, instead of segments, it's going to be definition of congruent, and we can use that symbol, angles. How was that? Not good. Okay, what I'm going to show you, give me a second here, on my JAG, I think I have it on my JAG.
It still was like the same thing where it didn't make sense because you would never need to prove that. You never need to prove that they're equal to each other because it says they are both right angles. They're both the same thing and they're both congruent. So basically what you're trying to do is you're trying to show to someone that doesn't know what congruent means.
Exactly.
That it's congruent.
That's the perfect way to describe it. You have to prove it's like what you're trying to do is teach someone who has no knowledge of geometry, doesn't know what a right angle is, right? You're trying to justify with every step. So to you, it's obvious that if you have two right angles, of course they have to be congruent. But you're trying to write out step by step, justifying, so you could explain to someone who has never heard of a right angle in their life. Right? And I know it seems like a bit much, but that's what we have. Okay. So if you go to your chapter 2, in the top right, geometry proofs reasons. Okay. Okay, hold on. Oh my goodness, it's just a list of things. It's just a list of things.
That's what's scary.
And like more than half
But
of
it's a lot of things.
More than half of them we've already done.
Oh,
okay. Remember that statement side and then the reason side?
Yeah.
These are all the possible reasons that we will be doing for chapter 2.
So there's no other reasons we could use only these.
No. So have we already done definition of congruent segments?
Yes.
We've
So
got
congruent angles, huh?
Okay. Do you see all of these? What I would encourage you to do is make flashcards for each of these.
Every single one.
Okay, it's not that many. Let's see.
That's like 25.
That's like less than our English test.
That is less than our English test.
There's 22.
Oh, that's
22 flashcards.
3 off.
So what I would like you to do is put definition of congruent segments, and you might have already done this because we had them from chapter 1, and then on the back, write out what does that do, right? What's the definition of an angle bisector?
Something that's congruent.
It divides an angle into two congruent angles. All right, we have a little bit of time.